Myself, Dr. Aditi Chatterjee from EC department. So today I'll be giving a lecture on transient analysis from network theory. So transient analysis, in that the basic components which a network comprises of are resistor, inductor and capacitor. Inductor and capacitors are the energy storing elements. So here in inductor and capacitor switches from one condition to another condition when there is change in applied source. So when there is change in the state of inductor and capacitor, the response of current and of voltage also changes from one state to another state. The time taken to change from one state to another state, which by state we means from initial steady state to a final steady state, is known as transient period. So transient period is the time taken for change from a initial steady state to a final steady state. Now this response means the response of change from initial steady state to final steady state is known as transient response. Now here we have basic components resistor, inductor and capacitor, which comprises the network. So R is denoted by R is the resistor, L is the inductor and C is our capacitor. Now suppose we have only resistor in our circuit. So let us consider we have applied voltage Vt. We are considering time domain representation. So the voltage across the resistor is Vt and the current flowing through the resistor is It. So how we will get the voltage across the resistor? Vt is equal to Rit. This is very common thing we have studied in Ohm's law also, V equals to IR. So it is just time domain representation of V equal to IR, that is Vt is equal to R into It. Now if we have inductor L and we have voltage across it Vt, we have applied voltage Vt across it and current flowing through the inductor is It. Then how we can get the current through the inductor? That is given by 1 by L integration of Vt dt plus I0. I0 is the initial current stored in the inductor. Now if we have a capacitor and let us consider the voltage across the capacitor is Vt and current flowing through the capacitor is It, then the current It through the capacitor is given by It equal to C dVt dt plus V0. V0 is the voltage stored in the capacitor. Okay, so here we have found how we can get the current across the current through the inductor and current through the capacitor. That is given by L integration of Vt dt plus I0. That is the initial current stored in the inductor, and V0 is the initial energy or initial voltage stored in the capacitor C. To the capacitor we can calculate by C dVt dt. Now if we want the voltage across the capacitor, then how we can get that? Vt equals to 1 by C integration It dt. And same if we want the voltage across the inductor, then how we can get that? Vt voltage across the inductor is given by L dit dt. So now suppose if you have a network which comprises of resistor, inductor and capacitor, you can calculate the current flowing through inductor, capacitor and resistor, as well as you can calculate the voltage across each of the elements also, inductor and capacitor. Now we will move to the next discussion, which are the initial conditions and usually when we have a network, we used to have a switch. So the switch is closed at a particular time t equal to 0. So the condition before is denoted by t equal to 0 minus, means before switching if the switch is closed at t equal to 0, so the before switching the time is denoted by t equal to 0 minus, and just after closing the switch the time is denoted by t equal to 0 plus, and steady state condition or the another time which we consider, that is t equal to infinity. So these are the time which we consider in the network analysis of transient analysis of networks. So we already know that our network comprises of basic elements: resistor, inductor which is denoted by L, and capacitor which is denoted by C. Now we have to consider that when the switch closes in the network, what are the condition or state of these elements like resistor, inductor and capacitor, because these are the basic elements. So we have to consider t equal to 0 plus, means the state just after the switch closes in the network, and we have to consider the steady state which is at t equal to infinity. That is the steady state, means what will be the state of resistor, inductor and capacitor at t equal to 0 plus, which is just after closing of the switch, and t equal to infinity means the steady state. So what happens to the resistor? The resistor will remain same, the value will remain same at t equal to 0 plus. Now means after just the switch closes. Now what happens to the inductor? After just the switch closes in the network, the inductor will act as open circuit. This you have to remember. And for capacitor, it acts as short circuit. Now for t equal to infinity, means under steady state condition, the resistor the value of the resistor will remain same, it is R. Now for inductor, at the steady state condition, the inductor will be short circuited, and for capacitor it will be open circuited. Okay, these three things are very important, and you should remember this for doing the numericals. Means like if we consider that they require, means an inductor does not allow abrupt change in the current through it. There is basically, if there is no current flowing through the inductor at t equal to 0 minus, means just before the switch closes, if there is no current flowing through the inductor, then at t equal to 0 plus, it will act as open circuit. If there is no current flowing through the inductor at t equal to 0 minus, then at t equal to 0 plus, it will act as open circuit. And similarly, if at t equal to 0 minus there is no voltage across the capacitor, then at t equal to 0 plus it will act as short circuit. Okay. Now if through the inductor at t equal to 0 minus, if a current I0 is flowing through it, then at t equal to 0 plus it will act as a current source with current I0 ampere. Okay. Now same goes for capacitor also. If the voltage across the capacitor is V0 at time t equal to 0 minus, then at t equal to 0 plus, it will act as a voltage source of voltage V0. Okay. Now for t equal to infinity, means at steady state condition, when we have element with initial condition inductor with initial condition of current I0, then at steady state it will be, the equivalent circuit will be a current source of I0, and we will have this equivalent circuit. Now if we have that will be short circuited, because inductor at t equal to infinity is short circuited. So I0, if the initial condition for an inductor with current source I0, then at t equal to infinity, the I0 will be there and the line will be short circuited at t equal to infinity. Now, if we have a capacitor, so under steady state condition, what will happen? There will be a voltage source of V0 and there will be a open circuit. So the equivalent circuit at t equal to infinity will look like this one: voltage source and open circuit. Okay. So we have got the steady state equivalent circuit for all the components: resistor, inductor, capacitor with initial conditions 0, and inductor, capacitor with initial condition I0 and V0. Apart from that, what we have got? We have got what will be the, means if we have a switch which closes at t equal to 0, then at t equal to 0 plus, what will be the state of the the resistor, inductor, capacitor, and again the inductor and capacitor with initial current I0 and initial voltage V0. So these are the main theme for doing network analysis problems or transient analysis problems on networks, given network. So now we will move to a numerical. So for doing the numerical, you have to remember which will remain, means what will be the state of inductor, capacitor at steady state, means at t equal to infinity, and at t equal to 0 plus just after the switch closes. So here you can see the first numerical, which is in the network. This is the network which you can see in the figure. The switches, this is the switch which closes at t equal to 0. Assume all initial conditions as 0, means there is no energy stored in the capacitor and there is no current, means the inductor, that for inductor also the initial current stored in it is 0 and the initial voltage stored in the capacitor is 0. So the initial conditions are 0. Find I di dt, d2I dt2 at t equal to 0 plus. So at t equal to 0 minus, we need to know what will be the current and what will be the voltage. Now it is written here in this numerical, assume all initial conditions are 0. So obviously there is no charge stored in the inductor and the capacitor, and the switch is open. So obviously no current is flowing through the elements, inductor, capacitor and resistor. There is no current flowing through it and the circuit is open. So obviously the current will be 0. So I0 minus. I0 minus means the instant when the switch is not yet closed, the switch is open. So obviously the current and the voltage, means the initial current and the initial voltage before the switch closes will be 0. So both IL0 minus and V0 minus will be 0. So at t equal to 0 minus, we have opted that the current and the voltage will be 0. Now we will find what will happen at t equal to 0 plus. Now for this we need to know what happens to the inductor and the capacitor at t equal to 0 plus. So that we have already, you have to memorize or you have to know that what happens at t equal to 0 plus, the inductor is open circuit and the capacitor is short circuited. These two things you have to know before you analyze the circuit. So we have to redraw the circuit at t equal to 0 plus. So what will happen? The inductor, here we have the inductor that will be open circuited and the capacitor will be short circuited. Right? So at t equal to 0 plus, you have to redraw the circuit and the circuit obtained is this one. We have the resistor as it is, the switch is closed now at t equal to 0 plus. The inductor will be open circuited and the capacitor will be short circuited. Now what will happen to the, now we have to find the current in the network and the voltage. Obviously as there is open circuit, so no current will flow through the circuit. So I0 plus will be 0 and V0 plus will also be 0. Now we have to find the steady state, because steady state means t equal to 0 plus to infinity, the time instant. So for at t equal to greater than 0, means for t greater than 0, we can redraw the circuit like this one. So the at t equal to, for t greater than 0, the switch will remain closed. We have a resistor in our circuit, we have an inductor, and we have a capacitor. The values are given by 10 ohm, 1 Henry for inductor, and for capacitor it is 10 microfarad. The applied source voltage is 10 volt. So now we have to apply KVL for calculating the current. The current flowing through it, let us consider I. So how we can get the equation by applying KVL. So how we will do that? Here we have 10 volt. So 10 volt, then we have R into I. So 10 into I minus L di dt minus, but for the capacitor it is 10 microfarad, and 10 microfarad means 10 into 10 to the power minus 6 farad. So we have 1 by C integration of I dt, 1 by C integration. So C we can replace by 1 by 10 into 10 to the power minus 6, and here L we can write 1. So this is our equation, 10 minus 10I minus di dt minus 1 by 10 into 10 to the power minus 6 integration of I dt. So if we rewrite this, we will be having 10 equal to 10I plus di dt plus 10 to the power 5 integration I dt. So we are having this equation. So we can consider this as equation 1. Okay. So this we are getting by applying KVL. Now what we need to know? We need to know what are the requirements of the numerical, that we have to find I di dt, d2I dt2 at t equal to 0. In some numericals you may find that it is given, find I0 plus di0 plus dt and d2 I0 plus dt2. So these two are same thing. Means when you find I di dt, d2I dt2 at t equal to 0 plus, and if you are asked to find I at 0 plus, di dt at 0 plus, and d2I dt2 at 0 plus, both are same thing. So you have to do the same thing. So these are the now requirement of the numerical. So we have got the equation. We have find that the I0 plus we have got 0 ampere. Now we need to know what will be the value of di dt at 0 plus. So in this equation, if we find it for t equal to 0 plus, then we will get the di dt. So we have this one. So if we find that for t equal to 0 plus, then it will be 10 equal to 10 into I0 plus di dt 0 plus 0, as I0 plus is 0. So if we put here 0, then this term will become 0, and we will get di 0 plus dt as 10, because here this will be cancelled as it is equal to 0. Here we have an integration of 0, so this term will also be 0. So we are getting di 0 plus dt equal to 0. And what will be the unit? Unit will be ampere per second, because here we have current by T. So ampere per second. The unit of current is ampere per second. So we are getting di0 plus dt as 10 ampere per second. Now we need to know what will be the d2I dt2. So for that, what we have to do, we have to differentiate this equation. We have this equation from the previous page. By applying KVL, we have got this equation. Now if we differentiate this equation, we will get d2I dt2. So now if we differentiate this equation, this is differentiation of constant, so this will be 0, then 10 di dt plus d2I dt2 plus 10 to the power 5 I. So this is our equation after differentiation. 10 di dt plus d2I dt2 plus 10 to the power 5 I. So this is our equation. Now we have to find d2I dt2 at I0 plus. So in this equation, d2I dt2 is equal to what will happen at t equal to 0 plus. We have I0 plus equal to 0. So this, if we put here I0 plus, this term will be 0, and we have obtained our di dt at I0 plus as 10 ampere per second. So d2I 0 plus at dt2 is minus 10 into 10, as di dt is 10 ampere per second, minus 10 to the power 5 into 0, as I0 plus is equal to 0. So what we are getting? We are getting minus 100 ampere per second square, because here we have dt2. So what we have obtained here? I0 plus as 0, di dt as 10 ampere per second, and d2I dt2 as minus 100 ampere per second square. So this is the solution of your first numerical. Now we will move to our second numerical. So in this numerical, we have this network, and the switch position changes from 1 to 2. The switch is changed from position 1 to 2 at t equal to 0. Steady state condition reached before switching, means when the switch moves from 1 to 2 at t equal to 0, before that steady state achieved. So we have to consider those conditions of the elements, passive elements, inductor, capacitor at t equal to infinity. Steady state means t equals to infinity. We have to consider inductor and capacitor, what are its state at t equal to infinity in our circuit. Then we have to find I di dt, d square I dt square at t equal to 0 plus. So in some numerical, you may find that they are asking for to find the I at 0 plus, di dt at I0 plus, d square dt square at I0 plus. This may be asked. So this is our network where the source voltage is 30 volt. Apart from that, we have two resistor, one is 20 ohm, another is 10 ohm, and we have a capacitor of 1 microfarad. So when the switch was at the position 1, that time steady state was reached. So under steady state condition, what we have seen, that capacitor, let me show once more. The capacitor at t equal to infinity is open circuit. Now if there was a voltage, it stores that energy. So here 30 volt was applied. So obviously the capacitor has been charged up to 30 volt. So in this numerical, at steady state, the capacitor will be open circuited and the energy stored or the voltage stored in the capacitor at t equal to 0 minus will be 30 volt. So Vc at means the voltage in the capacitor at t equal to 0 minus will be 30 volt. Now, as the capacitor is now open circuit at t equal to infinity, so the current through the circuit at t equal to 0 minus will be 0. So the voltage here, the capacitor is open circuit with a voltage of 30 volt and the current through it at t equal to 0 minus through the circuit is 0. Now we have to consider other two time instant t equal to 0 plus and t equal to infinity. Now at t equal to 0 plus, the capacitor is open circuit at t equal to infinity, that we have seen. So at t equal to infinity, the capacitor is open circuit with resistor 20 ohm and voltage, source voltage 30 volt. So I have written here once again, Vc 0 minus will be 30 volt and I 0 minus will be 0 ampere. Now when the switch moves to position 2, what happens? This switch moves to position from 1 to 2. Now the circuit will be comprises of this. There will be two resistors, one is 10 ohm, another one is 20 ohm and a capacitor of 1 microfarad. Now that has stored the voltage, that has the voltage 30 volt. So that will now at t equal to 0 plus, it will have a source voltage of 30 volt and the capacitor will be short circuited. That we have seen that at t equal to 0 plus, capacitor is short circuited and apart from that we have a voltage V0 source voltage of 30 volt. So here in this part we have only source voltage 30 volt. Now this 30 volt will be applied across these resistors. So now we can find the current. How we can find the current? The equivalent resistance is 30, 10 plus 20, 30. So now we can find the I0 plus. So that will be minus 1 ampere. Okay, voltage is 30 volt and the total equivalent resistance is 30 ohm. So the current we get minus 1 ampere. Now for t greater than 0, again we have the switch at position 2. So now we have resistance, we have these two resistance 10 ohm and 20 ohm. And apart from that, for t greater than 0, there will be the capacitor with 1 microfarad, capacitance and voltage of V0, which is V0 minus means 30 volt. This is 30 volt. So we have 30 volt source voltage which is stored in the capacitor and the capacitance of 1 microfarad. Now in this circuit, if we apply KVL, we will be getting the equation with I. Now once you get the equation with I, if you differentiate, you will get di dt. So we have already got I0 plus. Now if we apply KVL in this circuit, we will be getting this equation. Minus 10I, this is the voltage across the first resistor. Minus 20I, which is the voltage across the second resistor. Then 1 by C integration of I dt. The capacitance is 1 microfarad. So 1 by 1 into 10 to the power minus 6 integration of I dt and minus 30. Okay. So that equal to 0. So this we are getting by KVL. Now if we simplify this equation, we are getting minus 30I minus 10 to the power 6 integration of I dt minus 30. So this is our equation 1. Now what we get minus 30 d2 I dt square minus 10 to the power 6 di dt equal to 0. So d square I dt square is equal to 10 to the power 6. We here we will have a minus. We have 0.33 dIdt at t equal to 0 plus we have 0.33 into 10 to the power 5 ampere per second. Now simply we will put this value 0.33 into 10 to the power 5 here, and we can get d square I dt square at t equal to 0 plus. So at t equal to 0 plus, which is our d square I 0 plus dt square is equal to 10 to the power 6 by 30. We will get in minus into dIdt, and if you calculate this, we will be getting 1.1 into 10 to the power 9 ampere per second square. So this is the solution. Here we have got I at t equal to 0 plus as minus 1 ampere, then di 0 plus dt as 0.33 into 10 to the power 5 ampere per second, and d square I 0 plus dt square as 1 minus 1.1 into 10 to the power 9 ampere per second square. So this is the solution for this numerical. Thank you.